The core of our planet is currently behaving erratically. First, it appears to suddenly change its direction of rotation, then scientists discover mysterious structures deep within it. And as if that weren't enough, our planet is also cooling much faster than expected. What on earth is happening beneath our feet? Today we reveal the spectacular discoveries from the Earth's interior that could change everything we think we know about our planet. Be sure to stay tuned until the end. Welcome everyone. Imagine waking up one morning and discovering that the Earth is suddenly spinning in the opposite direction. Sounds crazy? Well, that's exactly what's happening right now, only not with the entire Earth, but with its core. Let's start with a discovery that has even experienced geophysicists completely perplexed. Beneath us lies a mysterious world about which we still know very little. I'm talking about the interior of our Earth, the Earth's crust, the Earth's mantle, and the Earth's core. And when I say its own world, that's no exaggeration. The Earth's core is about the size of Pluto. So we're really talking about a gigantic, unexplored realm of depth here. You might wonder why the Earth's core is so unexplored. It's close to us. Part of our planet, that's true, but we still can't get there and can therefore only explore it indirectly. The deepest hole ever drilled was the Kola borehole in the Soviet Union, which began in 1970 and reached an impressive depth of 12,262 meters. That is truly a remarkable achievement, but unfortunately still very far from the Earth's core. The core begins at a depth of 2,900 kilometers. The Kola borehole would have had to go more than 200 times deeper to reach it. We cannot dig down to it and explore it directly, but we can do so indirectly. Seismic waves, such as those triggered by earthquakes, are particularly helpful in this regard. These waves travel through the different layers of the Earth, and by analyzing them, geophysicists can draw conclusions about the nature of the different layers. Chinese researchers have conducted a large-scale study of such seismic waves in recent years and have come to a conclusion that is as clear as it is alarming. The Earth's core has stopped rotating. The government is probably already considering introducing an Earth's core rotation tax. So how did the researchers come to their alarming conclusion about the Earth's core? First of all, we are talking about the inner core, which consists of solid iron. Surrounding it is the liquid outer core. After decades of seismic research, geologists have come to the conclusion that the inner core oscillates, meaning that it rotates in one direction and then the other over a certain period of time. Researchers at Peking University examined seismic data from the 1990s and 2000s that originated from earthquake pairs. Earthquake pairs are also known as seismic doublets. These are two earthquakes that had almost the same magnitude at the same location at different times. If the analysis then shows that the seismic waves of the two earthquakes still differ, then the cause must lie deeper, much deeper inside the Earth. And the researchers found that in seismic doublets between 1995 and 2008, the seismic waves differed significantly from each other. However, between 2009 and 2020, there was a high degree of consistency between the earthquake pairs. This means that something must have happened around 2009. The inner core of the Earth has been rotating eastward since the early 1970s faster than the Earth's surface. Around 2009, the rotation paused and is now reversing direction. Overall, this probably points to a roughly 70-year movement rhythm of the Earth's core, which researchers refer to as super rotation. This naturally raises the question, is this dangerous for us? It could have a few effects. Researcher Xiaodong Song says that if the oscillation model is correct, we expect the inner core to rotate more slowly than the Earth's surface by the mid-2040-50s. And the whole thing will probably even affect the length of the days, i.e., the duration of our planet's own rotational movement. The days on Earth will become 0.01 milliseconds shorter. If the inner core rotates in a westerly direction, it will move eastward, the direction in which the Earth also rotates, and a day will become 0.12 milliseconds longer, but these are minimal effects that are imperceptible to us. Much more noticeable is the Earth's magnetic field, which acts as a protective mechanism against the sun's high-energy radiation and is created in the first place by processes in the Earth's core. Could the slowing down of the Earth's core endanger the magnetic field and perhaps even cause a pole shift, which has been talked about a lot lately? We have to distinguish between the inner and outer cores of the Earth. This is because the magnetic field is formed by processes in the liquid outer core. Seismologist John Vidal says that some people argue that the presence of the inner core makes it difficult for the magnetic field to reverse. We know that the magnetic field changes polarity every few million years, but this has no influence on the annual movement of the inner core. In other words, the existence of our planet's inner iron core stabilizes the magnetic poles, but its rotational movement probably has nothing to do with the reversal of the magnetic north and south poles. So the stopping of the Earth's core will probably not immediately bring about an apocalyptic pole shift, but this 70-year oscillation cycle also seems to apply to other layers of the Earth and is probably caused by an interaction between magnetic processes and the gravity of the Earth's mantle. What I find super interesting is that this 70-year rhythm is also found in many other terrestrial processes, especially in the climate. Global mean temperatures and sea levels also show subtle fluctuations in 70-year cycles. The research paper states that this periodicity of 60 or 70 years seems to indicate a resonant system. Our findings could therefore point to dynamic interactions between the deepest and highest layers of the Earth system. I feel that we do not yet fully understand many of the processes associated with the Earth's core that affect our entire planet. But this is just the beginning of our journey into the Earth's interior. While scientists are still trying to understand the enigmatic behavior of the core, other researchers have made an even more exciting discovery. Between the Earth's core and mantle lies a mysterious structure that completely overturns our understanding of the planet. At the boundary between the Earth's core and mantle, there is a previously undiscovered layer that is ancient ocean floor littered with gigantic elevations. A team of researchers from the University of Alabama used a novel analysis technique to record seismic waves near the South Pole that traveled through the Earth's interior from earthquakes on the other side of the planet and were finally picked up by measuring stations in Antarctica. The researchers were astonished when they evaluated the results. Dr. Edward Guarnero, one of the researchers involved, says that when analyzing thousands of seismic recordings from Antarctica, our high-resolution imaging method found thin, abnormal zones of material in the CMB wherever we probed. CMB stands for core mantle boundary, i.e., the boundary between the Earth's core and mantle. What could this be? The researchers immediately had an idea. It is probably submerged ocean floor that has gradually covered the entire area between the core and the mantle. Where tectonic plates meet under the ocean, huge deep-sea trenches are formed, such as the Mariana Trench. When these plates collide, it is called subduction, and over long periods of time in the Earth's history, one plate slides under the other. In the Mariana Trench, for example, gigantic amounts of water are sucked into the Earth's interior in this way, passing through a relatively unknown underground cycle and being spat out again from deep-sea volcanoes at another point in the ocean. This entire process may also have played an essential role in the origin of life, as it is believed that the first organisms arose in precisely such deep-sea volcanoes. Now, it also appears that these sunken seafloors have formed their own layer inside the Earth over time. Scientists call this the ULVZ, which stands for ultra-low velocity zone, i.e. areas of the core mantle boundary where seismic waves suddenly travel extremely slowly. Until now, it was assumed that these ULVZs only occur in small patchy areas, but these new research findings indicate that the entire core mantle boundary is covered by an ultra-low velocity zone due to the sunken seafloor. The lead author of the recently published study, Dr. Samantha Hansen, says that seismic investigations such as ours provide the highest resolution representation of our planet's internal structure. And we are finding that this structure is far more complex than previously thought. ULVZ regions are very irregular, as the data shows that their thickness varies between 1 and 10 kilometers. So we have found anomalies between the Earth's core and mantle that were created by sunken ocean floor and formed gigantic mountain ranges inside the planet. And that is important for understanding the overall geophysical system of our planet. These mountains inside the Earth could play an important role in how heat escapes from the core. And that is, after all, the part of the planet that drives the magnetic field. The Earth's magnetic field, in turn, protects us from the dangerous and high-energy particle radiation of the sun. This could pose a threat to us in the future if a pole reversal were to occur, i.e. if the magnetic poles were to reverse, causing the Earth's magnetic field to go completely haywire for a long period of time. The better we understand how the Earth's core works, the more certainty we will have regarding such magnetic apocalypse scenarios. This naturally raises the question of how we can find out more about this. Seismic data is, of course, always only indirect observations, and digging there would be very difficult. But what if we simply stood next to a volcano and waited for material to be spewed out of the ultra-low velocity zones? No joke, material from the ancient ocean floors can be carried away in mantle plumes or hotspots, which then return to the surface through volcanic eruptions. Sometimes science is just that simple. By analyzing the material from certain volcanic eruptions, we could actually obtain information about this mysterious world beneath our feet. I think Dr. Samantha Hansen put it very nicely. There is still so much we don't know about the world beneath our feet, and even small-scale structures like the ULVZs we've recorded can play an important role in how our planet functions. I'd be interested to know which of these places you'd most like to explore completely if you could. The Earth's interior, the ocean floor, or an alien exoplanet? Write your answer in the comments so we can turn it into a representative poll. These ancient structures from the sunken ocean floor are fascinating enough, but it gets even better. While studying earthquake waves, seismologists have discovered something that completely overturns our previous understanding of the Earth's core. They have, and now hold on to your hats, discovered a whole new Earth's core. The Earth consists of three main layers: the crust, the mantle, and the core. These layers have different densities and chemical and physical properties, which are influenced by geological processes such as plate tectonics and volcanism. Today, we are primarily interested in the Earth's core, the innermost layer, which consists of iron and nickel and has a pleasant temperature of around 5,500 degrees. Until now, geologists assumed that the core could be divided into two areas, the liquid outer core and the solid inner core. At least that's what we thought until now. Australian researchers have discovered something different based on seismic measurements. They measured seismic activity at several earthquake epicenters at opposite points on the Earth and found that seismic waves traveling through the innermost segment of the Earth, which consists mainly of iron and nickel ore, behaved slightly differently than in the layer above. But how can we extract accurate information from such seismic waves? The key word here is anisotropy. Basically, this just describes the fact that the properties of a material or system vary in different directions. A simple example is wood. Wood is anisotropic because it has different properties in different directions. For example, it is usually stiffer and more resistant in the longitudinal direction than in the transverse direction. The same is true of the Earth's core. When seismic waves pass through the Earth's core, they behave anisotropically because the physical properties of the core vary in different directions. In particular, the speed at which seismic waves travel through the core depends on the direction. In wood, the anisotropy depends on the orientation of the cell walls, while in the Earth's core, the anisotropy arises from the orientation of the crystals or molecules in the core's materials. But the principle remains the same. Around 200 earthquakes with a magnitude of over 6 on the Richter scale was studied, with a particular focus on a 7.9 magnitude quake that shook the Pacific nation of Solomon Islands in 2017. This earthquake was particularly well suited for studying the Earth's core, as the pressure waves it generated spread throughout the entire body of the Earth and were then recorded by numerous measuring stations on the opposite northern hemisphere. The researchers write that their findings strengthen the evidence for an anisotropically distinguishable innermost core and its transition to an outer shell, which could be a fossilized record of a significant global event in the past. For normal people, i.e., non-geologists, they have discovered a mini-core within the Earth's core, i.e., an innermost inner core surrounded by the inner core, which in turn is surrounded by the outer core. It's a bit like those Russian Matryoshka dolls, where there is always a smaller doll inside the other one. So there is a separate small core that is clearly separated from the inner core. Unfortunately, the terminology is now very confusing, and I think innermost inner core is a rather silly description, but unfortunately there is no better name yet. If you have an idea for a more appropriate name for the innermost inner core, please feel free to write it in the comments. In any case, the researchers were also able to obtain detailed information about the innermost inner core from the evaluation of the seismic data. It is about 650 kilometers in size and consists of pure iron. This raises new questions. If both the innermost inner core and the inner core consist of solid iron, why did two separate structures form in the first place? This now needs to be investigated further, so it remains exciting. Researching the Earth's core is important for understanding more about the formation and development of the Earth, and also about how our planet's magnetic field works. The Earth's magnetic field is largely caused by effects in the Earth's core, which is called a geodynamo. As we already know, the outer core of the Earth is liquid and the two inner cores are solid. The movement of these electrically conductive fluids around the inner cores creates the magnetic field. The newly discovered innermost core could therefore revolutionize our understanding of the Earth's magnetic field, which in turn could provide us with important information about the reversal of the magnetic poles known as the pole shift, which will occur at some point in the future. The research paper states that although the geomagnetic field may have preceded the birth of the inner core, changes in the structures of the inner core may indicate shifts in the geomagnetic field that could have profoundly influenced the evolution of the Earth and its ecosystem. And the Earth's interior holds even more surprises. Deep inside the Earth lies a truly cosmic treasure, a reservoir of helium-3, an isotope that is almost as old as the universe itself. Helium-3 is known from many science fiction films as a coveted resource on the moon, but now researchers have found a gigantic amount of it inside our Earth. Around 2 billion tons of this primordial isotope helium-3 are bound in the metal of our Earth's core, and that is truly an amazing discovery, because helium is relatively rare on Earth, even though it is the second most common element in the cosmos. This is because helium is produced in stars like our Sun, where it is created during nuclear fusion when hydrogen fuses into helium. But on Earth, it is relatively rare, and the reason for this is obvious. Helium is extremely volatile. When it is released, it rises to the top and is not held back by Earth's gravity. However, terrestrial helium reserves can be stored in underground cavities. It was already known that there was a certain amount of helium there, because helium escapes from many volcanoes, but no one expected 2 billion tons. This raises the question of how this amount of helium got there. The atoms of the helium-3 isotope were formed shortly after the Big Bang. Such isotopes are called primordial, meaning they were there from the beginning. This means that helium-3 was not created by processes inside the Earth, but that the Earth must have collected it when it was formed. About 5 billion years ago, the Earth was formed in a gigantic protoplanetary disk, a huge accumulation of dust, gas, and small rocks that was still revolving around the young sun. In this protoplanetary disk, the Earth probably collected huge amounts of helium-3, which has been slumbering inside it ever since. So far, so unmysterious, but now it gets tricky because the Earth had a bad accident in the past. It collided with a planet called Theia, which was about the size of Mars, and in this collision, a large piece of Earth broke off, which eventually formed the Moon. Shouldn't all the helium stored inside Earth have escaped during this planetary crash, which probably happened about 4.5 billion years ago? After all, Earth had a huge hole in it after the collision. So how did the huge helium-3 reservoir in the Earth's core survive the collision? The answer has now been found by researchers at the University of New Mexico, who have used laboratory experiments and geophysical models to discover that the helium-3 reserves must be located very deep in the Earth's core, so deep that they were protected from the collision with Theia. And the reason for this deep location can be found in the conditions of the then still very young Earth. At that time, our planet was uncomfortably hot. The Earth was covered by huge oceans of lava with no sign of life anywhere. Not only did the Earth's surface look different than it does today, but so did its atmosphere. It contained significantly more helium, and helium from the dense primordial atmosphere of the young Earth constantly mixed into the lava ocean, i.e. the molten rock. When the lava ocean eventually cooled, a lot of helium remained bound in the now solid rock, but some of it probably sank even deeper. Researchers at the University of New Mexico describe it as follows. Experiments show that only a small proportion of the helium dissolved in the silicon melt passed into the iron-rich fluids as they sank through the magma ocean. But this small amount was enough to transport substantial quantities of helium-3 into the proto-Earth's core. And while most of the helium bound in the rock was ejected into space by the collision with Theia, the portion of helium that sank into the Earth's core remains there to this day. So far, so good. But the exact processes between the Earth's core and mantle are still relatively mysterious. For example, does helium exchange occur between the core and mantle? Researchers believe that, in addition to factors such as temperature and the nature of the core-mantle boundary, this depends primarily on the concentration gradient between the two layers of the Earth. There is therefore a constant exchange of helium between the Earth's core and mantle, and the helium that is eventually emitted by volcanoes probably originates from the core. The research team writes that it is a miracle of nature and a key to the history of the Earth that significant amounts of this primordial isotope are still present in the Earth's interior. The collision with Theia and the resulting primordial helium in the Earth's core is truly science fiction that has become reality. But while we are still marveling at these cosmic events, Swiss researchers have made a discovery that is even more important for our future. They found that our planet is cooling at a rapid pace from the inside out. And this heat, which flows out from the interior of the planet, is immensely important. It is the basis for geological processes such as plate tectonics and volcanism, and above all, it keeps the geodynamo of our magnetic field running. Conductive matter, mainly molten metal, rotates in the outer core of the Earth. This mass of molten metal surrounds the inner core, which consists of solid metal. This creates a current that generates the Earth's magnetic field. And this magnetic field is self-sustaining. Without it, the Earth would be much less hospitable to life and would probably resemble Mars today. This is because the geodynamo generates the Earth's magnetic field, which protects the Earth's surface from bombardment by cosmic rays and solar wind. We therefore have a strong interest in ensuring that heat continues to be produced in the Earth's core and penetrates the outer layers. And a team of researchers at ETH Zurich, led by physicist and geochemist Professor Motohiko Murakami, has now made the alarming discovery that the Earth is cooling much faster than previously thought. Murakami says that our findings could open up a new perspective on the development of the Earth's dynamics, suggesting that, like the other rocky planets Mercury and Mars, the Earth is cooling down and becoming inactive much faster than expected. But let's take a look at how the research team arrived at its findings. The heat reservoir in the Earth's core is not inexhaustible, of course, because otherwise it would be a kind of perpetual motion machine. Heat escapes to the outside, causing the Earth's core to gradually cool down. The question is how quickly this happens, and the so-called core mantle boundary is crucial in this regard. This is where hot molten metals from the outer core, mainly iron and nickel, meet the rock of the mantle, which is around 1000 degrees cooler. You can imagine it a bit like the area where hot volcanic lava flows into the cold sea. Except that the core mantle boundary is, of course, a much more distinct boundary. It is actually the largest thermal boundary on our planet, and it is precisely at this boundary that it is determined how much of the heat from the Earth's interior can escape to the outside. In other words, to find out how fast the Earth is cooling, we need to find out how much heat is being absorbed at the boundary between the core and the mantle. And to do that, the research team from Zurich came up with something very, very clever. They took a closer look at the mineral that predominates there. The Earth's interior is home to a whole host of curious minerals that can only form down there due to the immense pressure. One of these is bridgmanite. This is basically only found in the Earth's mantle and on the surface, at most in enclosed meteorites that struck the Earth at some point. Bridgmanite is the dominant mineral in the core mantle boundary, and until now, there has been considerable debate about how well it conducts heat. As we've already seen, the problem is that we cannot simply dig down to the core mantle boundary and examine the bridgmanite there. Therefore, the researchers did the following. They simply created bridgmanite crystals themselves, using extreme high pressure and heat under laboratory conditions. They placed one of the crystals in a diamond anvil cell and subjected it to a pressure of 80 gigapascals. Using a laser, they then heated the crystal sample to around 2200 degrees Celsius. In principle, the researchers recreated the conditions at the core mantle boundary and used a spectroscope to record the radiation emitted by the crystal. From this, they were able to determine the heat flow, and state of the crystal. It's totally crazy that something like this is even possible, and the result was just as crazy. Bridgmanite dissipates heat 1.5 times better than previously thought. This means that the core mantle boundary allows much more heat to pass through than previously thought. The Earth's core cools down much faster. Not only will the Earth's dynamo give up the ghost earlier than previously calculated, but plate tectonics, continental drift, mountain formation, and volcanism will also come to a halt faster than previously assumed. How much faster? Unfortunately, we don't know yet because such geological processes take place over enormous periods of time and are very difficult to calculate. Other factors that play a role include the decay of radioactive elements in the Earth's core and the precise movement of what is known as mantle convection. So in summary, the Earth is cooling much faster than expected, the core is rotating backwards, mysterious structures run through the Earth's interior, and ancient helium tells the story of a cosmic collision. Our planet is truly full of surprises. I hope you are all now real experts on the Earth's core. I will, of course, keep you up to date on all new discoveries from the Earth's interior here on this channel, so if you haven't already, click on the subscribe button and remember to give us a thumbs up to really boost the YouTube algorithm. And with Christmas just around the corner, why not take a look at the Astro Shop? To get cool Astro-Tim shirts and other galactic stuff, click on the link at the bottom left. Every order really supports my work, otherwise, I'd say see you in the next video. Take care, folks.